Okay, in this video, I want to go over how we can find the area between curves given as a function of x. And in the next video, I'll show you how to find the area between curves when they're given as functions of y. And then in the third video, I'll show you how to find the area between curves that may have multiple intersection points. So we're going to keep on increasing the particular difficulty of this. And this section for you and your homework is broken up into really two homework sets. And we're doing the first half of it today, the area between curves given as functions of x. You've already been doing this, and I'll give you an example. Suppose I have some function of f of x, and let's just say it's between a and b. And if you want to find the area underneath that curve, you would integrate from a to b of f of x dx. And that will give you the area underneath that curve bounded above the x-axis. So let me actually color in. Let me use a different pen. Let me just look at, this is the top function, is f of x. The bottom function here, the function there, that's y equal to 0. That's another function. So we have y equal f of x. And you can think about, if I want to find the area underneath this curve bounded between those two functions, I need to figure out the height of my rectangle as I go from left to right. And that height is given by always by f of x minus 0. Keep that in mind as we're trying to find the area between two curves. Let me zoom in a little bit more. Okay. So I just have a picture here. Suppose we have a top function f of x, I'll call that the top, and we have a bottom function g of x. If I want to find the area bounded between these two curves, which I have in pink, then you have to figure out what the height of the rectangle is as I move from left to right. And if the height here is given by f of x, and the height here is given by g of x. So that means the height of the rectangle that I've written over here must be f of x, g of x at any arbitrary point x. And if I integrate all of those heights from a to b, I can then get the area of the rectangle. And that's it for finding the area between two curves. You got to identify what the top function is, what the bottom function is, integrate over our domain, and off you go. Now, in the next video, we're going to talk about what happens if this picture is sideways. Suppose I have something like this, and I'm trying to find the area between those curves. It may be easier if I rotated my paper and I made the height of my rectangles be vertical in this rotated regime or horizontal in that regime. And that would amount to finding functions expressed as y rather than as x. Anyways, let's look at a practice problem. Let me move my coffee over here. So we're going to find the area bounded by e to the x and x squared on the interval 0 to 1. The primary goal for you is you need to have a mental picture of what this scenario is. So I want you to make a picture of this. I've given that here. I have Desmos open, so let me just graph e to the x, graph x squared, and on the interval 0 to 1. And so I'm going to flip over to Desmos here. You can see I've specified e to the x. Okay, that's that top function. Let me turn off the shaded region. That's this top function right here. So that's the top. And the g of x is x squared over the region 0 to 1. Remember, this piece right here specifies the domain that you're expressing the function. This cool little cell right here just says, can you shade the region between g of x and f of x? That shaded region, let me put in a different color for you. Let me put it in orange. That shaded region is what we're trying to find the area of. And if we integrate from 0 to 1 of the bottom or top function minus the bottom function, we would then have a result of about 1.385. Okay. Now we can get an exact expression going back onto our notes here, but that's what we have here. The area integrating from 0 to 1 is the top function, e to the x, minus the bottom function. So we have to go the height of the rectangle. So the height of the rectangle is e to the x minus x squared at a given x value. Because remember, that height changes as the exponential goes off to infinity, and as x squared changes, that height changes. So it's okay to have a height that's a function. We integrate that. We're going to use one of our first rules of integration. We're going to integrate term by term. I'm going to integrate e to the x, which is e to the x. Antiderivative x squared is 1/3 x cubed. Evaluate between 0 and 1, and we end up with the expression e minus 1/3, and then minus the evaluation at 0, 1 minus 0. So that's why there's a minus 1 here. And we get this exact result, e minus 4/3. If I want to compare that to my approximation that I have here, I can go e minus 4/3. And we see the approximation here is the same thing as your approximate result there. This is exact. This is a computer rendering of an irrational number as a rational number. But those are in agreement, numerically at least. So let's look at our next example. I won't use Desmos here, okay? But you should be using Desmos to make this picture, okay? What I'm hoping is that you develop some good spatial acumen of looking at different functions that are given to you and to have this mental picture, okay, without having a calculator render that picture. Because we have to figure out, how do we know which one's the top function, which one's the bottom function? What's the area that we're calculating? And so we're finding the area bounded by this function, my = 4 from 3 to 5. Now I didn't say y equals, I'll put that in there to make it explicit. But the graph of 4 over 2 minus x is this little curve right there, and y = 4. And so my rectangles go from top to bottom. So 4 minus that expression would be the height of the rectangles, and that's what I have in the integrand of my integral, integrating from 3 to 5. Now, in this scenario here, it may be easier for you to factor in that minus in the denominator. And so to write I'm going to put the integral aside here. You'd have the integral of 3 to 5, 4 plus 4 over x minus 2. And the reason why that might be easier for you to look at, integral of 4 is 4x. The integral of 4 over x minus 2 is the natural log of x minus 2. Okay. I just left it as 2 minus x, but notice the absolute values will give me the same value that you have. Then I have the natural log of the absolute value of 2 minus x times 4, a value between 3 and 5, and I get this expression. So I plug in my 5, I plug in my 3, so I have 5 times 4 minus 3 times 4, that gives me a 4 times 2. And then in this expression, you can think there's a 4 all times that, so I just factored it out. There's a natural log of absolute value of 2 minus 5, that's just 3. Then I have 2 minus 3, which is natural log of 2 minus 3, which is natural log of 1, which is 0. And that's why I only get natural log of 3. Again, you can check this using Desmos as well, and I'll stop the video with that check. Okay, so let me integrate. So to get the integration symbol in Desmos, I'm just going int. That immediately gives puts a cursor on the lower bound. 3, I can tab to the upper bound. I can tab to the integrand. Since my integrand is going to have more than one function, it behooves me to use some parentheses here. But I have 4 minus 4 over 2 minus x. Let me end the parentheses there, end the parentheses, and you have to do dx to end the command. I got 12.395 or 4, sorry. And let me compare that to the exact result that we had in the notes. So we have 2 times natural log of 3, and we see we get agreement. And so the approximation agrees with the exact result. Okay. Well, what I want you to do now is to get into the 7.1 homework. It's broken up into, 7.1 homework has 2 parts to it. Finding area between curves that are expressed as functions of x. I'm going to follow up with another video of finding the area between curves that are bounded between functions of y.